And we can move to our second speaker, who is Victoria Price. She will be giving a talk on investigating a strategic aquifer storage and recovery scheme in the Sherwood sandstone to improve resilience from UK.
Hi, good morning. So like with many of these talks, I just wanted to say that I didn't just do this by myself. There are lots of people in our team, and this is work which we did for Anglian Water, who are a public utilities company in the UK. So a bit of background to what we had to do. Hannah Stanley-Jones gave a talk on the whole background, so if you saw that, then you can fall asleep for a second. In the east of the UK, it's designated as an area of drought stress or water stress, so it's quite constrained. There's lots of agriculture, there are a lot of people. And as a result, there's a need for a long-term plan. So 2080s is where this plan comes into. Water Resources East intends to take into account all sorts of different factors, including climate change, population growth, increased frequency of drought, and all of these different options, supply side and demand side, were sort of pulled together to kind of compare and get a few different options, hopefully using a robust decision-making approach. They used a water resources simulator to carry out this multi-criteria analysis, including economic factors. So how does that relate to ASR, or MAR? So ASR was identified as a potential option for supply. Our study area is in the green box in the east of the UK, so it's up near Yorkshire, in the Humber estuary. We had not a lot of ASR actually in the UK, and so a lot more investigation was required to inform the decision about this option, what the scheme design might be, how big it could be, and in turn inform the cost of the option. So this is the Sherwood sandstone. It's a nice red sandstone. It, in our study area, is confined by about 230 meters of Mercia mudstone, so it's quite deep. The water there in the confined zone is quite old, doesn't really move very much. The focus for this scheme, there were many different ASR options. The one that we're looking at here today is to supply during a severe drought, which is defined as an 18-month outage, essentially, from other sources. And I go into why that would be an issue in this area. Recharge water to supply the ASR scheme is from a nearby river. That river is subject to restrictions on abstraction. There are hands-off level, hands-off flow conditions on that, and this means that you wouldn't be able to just use that water during a drought. So here's our study area once again. You can see, hopefully you can see it at the back, that you've got a river flowing sort of north-south. That in the middle of the screen, the darker pink, that is our source water area. So that is quite a dirty river, to be honest. Requires quite a lot of treatment. There's pesticides, there's nitrates, there's industrial effluent. So there's a lot of need for treatment of that water. There's also some groundwater abstractions they take from the Sherwood sandstone, so like I said, confined by 230 meters of Mercia mudstone in the center, so the sort of round blue dots. I'm going to try this. Oh wait, it sort of does work. Very faintly. So, okay, so this is a big source here, which is used by Anglian Water to supply this city and the towns. You also have, over here on the left-hand side, in the light pink, this is where the Sherwood sandstone comes to outcrop. And you have quite a lot of environmentally sensitive sites. So the green, I'm really sorry if you're red-green colorblind, by the way. Anyway, there are darker areas here if you are these ones here. So these are sensitive sites. They're designated. There are restrictions on how much you can affect those. And these rivers here, which flow kind of along the outcrop, get a lot of base flow from the Sherwood sandstone. You have gauging stations, which we'll come back to later, which kind of control that. And these little dots here are potential ASR schemes. They don't exist at the moment. So this is our scheme, hopefully a bit clearer. You've got existing groundwater abstractions, so the brown stars, some of them in the unconfined Sherwood sandstone, some of them in the confined Sherwood sandstone. There are concerns, I should say these are subject to investigation, but there are concerns about the impact of those groundwater abstractions on these rivers. Remember the triple SIs, the dark green environmentally sensitive sites. So these, it is proposed that they might affect the flows in the river, most likely. And then you have further over here, you've confined, deeply confined, and you've got more groundwater abstractions with lower yields, it has to be said, than these ones. You've got the river, dirty river, and you've got a treatment works here, which is a surface water abstraction currently. So at the moment, this water here is blended with the groundwater here and then pumped to supply over. There's a city over here. So our proposal is to stick in some ASR boreholes, a well field, in total 18. This doesn't count up to 18. So abstract from the existing surface water abstraction plus one new one, treat at the current treatment works, then pump out these boreholes for a period of 5 years is what we're assuming, before you abstract again during your severe drought scenario. So investigations are really required to define the scheme a bit better. Not much is known about ASR in that area and hasn't been done. There's also a lot of concern from the Environment Agency on the impact of abstraction, particularly on flows in the rivers and on the triple SIs that we saw, so environmental sites. So we used the groundwater model. Just like to point out, we're very time constrained in this project. So there wasn't time for pilot studies. There wasn't time to go and drill boreholes or do field investigations. So we used a groundwater model to define the capacity of the scheme. That then informed the cost and the annualized incremental cost, so cost benefit, I suppose, to assess the impact of the scheme on the identified receptors, and to consider the potential movement of poor quality recharged water towards nearby abstraction boreholes. This comes back to the surface water abstraction, which is not that clean. It would be treated to potable standards, but there are potential issues with trihalomethanes in particular, which were causing concern. So this is our study area once again, in case you've missed it. We have a regional groundwater model here. The regional groundwater models in the UK are developed by the Environment Agency, often actually built by the consultants, people like me. They are time variant. They run from, this one runs from 1839. The Sherwood Sandstone is very slow to react, so any abstractions, the big abstractions in the sort of 19th century for industrial expansion are still having an impact right up until the mid-20th century. It comprises a regional recharge model, so that's a daily model which includes aspects of runoff for stream flow, as well as recharge to the groundwater, plus a mod flow model which is then used, then used to calculate the flow. So you've got a grid size of 200 meters by 200 meters, which is pretty standard for these models, and they include all the historical abstractions and surface water discharges. These are considered to be the best understanding of the hydrogeology in that area, and that's true of all the regional groundwater models. So it was decided that we would use that. It's also a tool which is developed by the Environment Agency, and therefore the results of that model would be hopefully accepted by the regulator. So just to zoom in to show where we are, you can see the pink, which is the unconfined Sherwood Sandstone, and then our study areas off to the sort of east, within the green, which is here. And that's the confined Sherwood Sandstone. So the scheme, this is what we proposed, that you could abstract about sort of 42 megalitres a day from surface water during the winter and stick it in the ground. So that's our recharge, and that for 5 years that would be fine. And then you'd have a severe drought, and during that severe drought you would abstract as much as possible from your ASR scheme. These numbers, the 42 megalitres a day of recharge and the 46 megalitres a day of abstraction, were refined during modelling, but also were controlled by specifics of, for example, the capacity of the water treatment works and the hands-off flow conditions on that surface water abstraction. So this is one of our boreholes, our ASR boreholes. This is what the model is saying. To start with, the green line is, again, here, just going across here, the straight line here, that's the modelled recent actual conditions. So essentially it's assuming that the groundwater will continue to be abstracted at exactly the same rate for all time, and that all other transient conditions will remain the same. This is with the exception of recharge, so this uses a historical recharge model. And then the red line at the top is ground level, and then down the bottom you've got the base of the Mercian mudstones at the top of the sandstone. So what you see is a large thickness of mudstone. Groundwater levels typically sort of around 25, 30 meters below ground. When you start recharging, you get water coming up above ground surface. So the limit to that was then 20% of the thickness of the Mercian mudstone, a relatively standard, I hope, approach, which is we got from Pine, the book. And then down the bottom, we did actually have a restriction on the minimum drawdown level. It turned out not to be an issue in terms of this model. That would be 10 meters above the base of the Mercian mudstone, which is the pump setting in most of these confined Sherwood sandstone boreholes. So in effect, whilst we did have some practical considerations in terms of how much could be recharged, the main constraint here is how much the boreholes could physically take. And we did a bit of refinement around this, like we moved some water around. Some boreholes recharged 0.5 megalitre a day, and other ones might recharge, say, more like 5 megalitres a day, depending on where they were. So we did a bit of optimization of the recharge and the abstraction time series. So yeah, again, we've got here, as I mentioned, the issues with regulatory approval on this is that they did not want to see any impact, particularly during a severe drought, on the flows in the streams and rivers across the unconfined. So what you see is the red and blue lines, which are the historical time series at this gauging station, and then that as a percentage of the modelled flows. So the difference between the two really is this green line in the middle, and that's on the right-hand side, this axis. You can see that during recharge we get about 5% increase in flows in those streams, and then during abstraction we get around, less than 5% was what we were asked to achieve. In this particular instance it is about 3.5%, 4% during severe droughts, and that's when you've got abstraction going on. So this is 1, 2, 3, 4, 5 cycles that we've got. So this is really demonstrating that there is an impact on those streams, but that impact is hopefully not significant in terms of the environmental flow indicators and WFD directive status of those sensitive bodies. So the final thing that we did is we looked at particle tracking. Like I say, dirty water, treated to a high level, then recharged. So we use ModPath and our flow to basically look at where that water would go to within the lifetime of the model. So in this case, what you can see is that really the water doesn't move very far away from where it's recharged. And if you do analytical calculations, that sort of stacks up. You've got quite high porosity, around 20%-ish, and it's a very thick aquifer. So at this point, I think it's more than 200 and 250 meters thick, and we're assuming that it is recharged over the full thickness of that. And that's typical for the boreholes, which are generally open hole below the base of the Mercian mudstone. So in conclusion, we used modelling to look at the strategic scheme for aquifer storage and recovery. It looks as if it would be possible to provide up to 46 megalitres a day for an 18-month extreme drought. We don't expect that recharge water to be transported very far from the boreholes, and the model's losses from sensitive environmental sites, including the streams, would not exceed 5%. Our recommendations really are, based on this, to do further investigations and pilot testing, to refine the model, inform the scheme design, and hopefully improve what could be a strategic scheme. Thank you very much.
Is there any question for Vittoria? Yes, please.
Thanks, Victoria. That's very, very interesting. Hugh Williams was from the UK, now in Spain. Just a quick, perhaps a comment and then a question. You said there weren't many ASR schemes in the Sherwood Sandstone. My thesis was called the limits of applicability of ASR in the Sherwood Sandstone. We drilled those wells about, when I was a student, so they've been licensed and operational for 15 or so years now, I think. But then the question I had was, you adopted the Environment Agency model, and you said that had 200 by 200 cell. How does that fit in with the model discretization? How does that fit in with the well field? Because you're reporting groundwater levels at the boreholes, but with the grid size of that relative to the spacing of the wells. Was there any refinement, or?
No, we didn't do any refinement. That is a possibility. It adds quite a lot to the runtime and the complexity of the model. What we did is that we had well loss calculations which were done for the existing groundwater sources. So in fact, we added well losses on top of the recharge head and the drawdown. It's not the best way of doing it. However, it probably is more conservative than refining it within that, sort of refining around that grid. And since our main concern really was these impact on across the unconfined outcrop on those streams, that was the focus of our study. And I think I am aware of your Sherwood Sandstone scheme. I think it's, yeah.
Mike, please.
Yeah.
Okay. Any other question? I have one for you. How did you simulate the ASR scheme? With imposing the head or imposing the flow?
We imposed flow. So we used the well file to have injection rather than abstraction.
Okay. Another question there. Please. Here.
Hi. What recharge model did you use to estimate groundwater recharge?
So in the UK, we use something called 4R, which is the routing of rainfall to runoff and recharge. It is it's based on the FAO methodology. So you have your soil moisture deficit and proportional amounts of runoff based on intensity of rainfall and antecedent soil moisture conditions.
Okay, it's like a soil-water balance or something like that?
Yes, it's like a soil-water balance, effectively. It's quite commonly used across the UK. There are essentially the same things available, which are available for free. ISMAR Mods 1. But this is what the Environment Agency require, and it's standard practice in the UK.
Because I've seen that you have a very large simulation period from 1939.
Yeah.
Have you done some uncertainty analysis to validate the weather data series? Temperature, precipitation for this long data period?
So I wasn't involved in the construction of this model. It is standard practice to use the Environment Agency's data sets, and they have their own verification for things like the input variables, which are potential evapotranspiration and rainfall.
Okay.
I think the main reason for using, going from 1839 and whether it's present, is that the kind of calibration historical period is from the 1970s onwards. And so that long run-in period is really required to get the initial conditions for the sort of period of time that we're interested in right. If you didn't have that long run-in time, the influence of those large abstractions would not be fully represented, and you'd end up with errors carried forward through into the historical modelling period.
Okay, thank you.
Any other question? Okay, for the last time I ask if there is anybody from the Lebanese team. Thank you, Vittoria, of course. Sorry. And I ask if there is anybody from the Lebanese team giving the talk Artificial Recharge of Karst Groundwater System in Developing Country? No. So I think we can close the session here. I wish to thank my co-convener Gudrun Massman for co-convening the session, you to be here. And there are still 2 sessions ongoing in the other rooms. One is the roundtable on water management and ICT, and the other one is MAR in coastal areas. The roundtable is in room 4, and the MAR in coastal area is in Sala 6. Okay, and there is also session 20 ongoing, is training on MAR, and is Sala 5. Okay, thank you for coming, and enjoy continuing the conference.